This video is going to show how to use DiadFit to perform calculations using the water CO2 equation of state of Duane and Zhang. So just to note, this was converted into Python based on the C code from this recently published paper. This was really groundbreaking for finding mistakes in the original typed equations in Duane and Zhang, so massive shout out to them, could not have done this without them. Okay, so there's two types of calculations that you might want to perform in DiadFit using this mixed equation of state. The first is, if you work with fluid inclusions, while it's nice to assume that they are a pure CO2 fluid, and you can use something like the Span and Wagner or the Stirner and Pitzer equation of state, in reality, you probably have some water in the fluid phase. So you can calculate a pressure if you can assume an H2O value, say from melt inclusions, and then we can also calculate the pressure using the mixed CO2 water equation of state, and that allows us to see how much is water affecting our calculated pressure. Now, the other situation is, say you're an experimentalist, you probably know pressure, temperature, and maybe H2O of your experiments, and you might want to use this equation of state to calculate molar volumes, compressibilities, activities, and fugacities. So this code can also do this. So the first thing you're going to have to do is install DiadFit. This is only available from version 81+. So you're going to want to uncomment that and upgrade your DiadFit installation. Next up, we load in the Python packages. So for calculating fluid inclusion pressures using H2O, we are following the theory laid out in Hansen and Klugel. And this is basically, you assume you trapped your fluid inclusion with some H2O, and it is then assumed that that H2O has been lost by the time you go and measure your fluid inclusion in the laboratory by either Raman spectroscopy or microthermometry. So the things that you have is you have the density of CO2 that you measured by either of these techniques. You have an estimate of the temperature, and now you also need an estimate of the mole fraction of water that was around. That is assuming that water is lost. You can also do the calculations assuming that water has stuck around, and the maths for that is laid out here and in the DiadFit paper, so I will refer you over to these. So let's move on to some calculations because you can read the paper for the theories. So say you measure a CO2 density of 0.3 and you think H2O is 0.1. Maybe this is based on melt inclusion data. So for example, the model MagmaSat by Gyorso and Gualda in 2015, which is available in the Python tool Vesical. This will tell you H2O in the exol fluid at the time of melt inclusion entrapment. So let's run this calculation. So we're running it at 0.1, so a mole fraction of 0.1 of H2O, a CO2 density, let's do that, of 0.3, a temperature of 1200 degrees, and then the other thing you need to give is the temperature you actually did your Raman measurement at if you want to assume that water has stuck around. So let's just run this and see what you get. Okay, so the code tells you the pressure using the Span and Wagner pure CO2 equation of state, the pressure using the Stirner and Pitzer pure CO2 equation of state, tells you the pressure using the equation of state in Duane and Zhang with no water, and then it tells you the pressure if you use the mixed water CO2 Duane and Zhang equation of state and you assume that water is lost, like in Hansen and Klugel. It also does the same calculation assuming water is not lost. And then what we show here is the ratio of sort of the pressure for water lost divided by the pure Duane and Zhang equation of state for CO2. So what this shows is that, the fluid pressure is 12%, 13% higher if you use the mixed equation of state. And then you can also just see the other things that we've calculated, like the bulk density that have come out from both assumptions, and then your input parameters as well. I'm going to change this quick because we've just run at a slightly different density. Okay, so this is great for one fluid inclusion. Say you want to visualize what this looks like in a different H2O space. So let's consider fractions of water between 0 and 0.2. And we're just going to consider 50 nicely spaced values between them using this NumPy lin space function. We're then going to perform the calculations. We're calculating entrapment pressure for a given H2O for every single one of these points, and then a CO2 density of 0.1 and a temperature of 1200. We're going to do the same calculation using a CO2 density of 0.2, 0.3, 0.5, 0.7, 0.9 and 1.1. Okay, so this is spanning really the range of CO2 densities that we see in fluid inclusions. And we're just going to store this in a dictionary to hold the value. So what we're particularly interested in is how the pressure that we calculate, assuming water and CO2 and that water has now been lost, divided by the pure equation of state, okay? So you can run that. Now, the more Pythonic amongst you will say, this isn't a very Pythonic way of doing this. Why are you typing out these lines? This is really just to help people that don't know Python. You can see very easily how you would expand this to more densities. Of course, in reality, you can write this in a loop. So you can ask it to loop over as many CO2 densities as you want. You could add more in here if you wanted to. And then we're just going to store, again, in a dictionary. So they give the same result. Okay, let's make a nice plot. So what we want to plot is we want to plot XH2O on the x-axis, and on the y-axis we want to plot the pressure that we get from the water CO2 equation of state divided by the pressure that we would get from the pure equation of state. Okay, so this is going to tell us if we didn't account for water, how wrong our density would be. So what we can see is here we have this plot. The different line colours are for different densities. And that is all set here, where you're basically setting a colour map. Don't worry too much about this if you don't like Python. If you do, if you want to know more, type it into ChatGPT. It can explain it to you. So you can basically see at lower CO2 density, so like 0.1 gram per centimetre cubed, really even like 20 mol% water is only going to change your pressure by about 20%. As you go to higher and higher densities, so more like 1.1 gram per centimetre cubed, actually the correction for water becomes much more. Okay, so far we've sort of done it for one fluid inclusion, and we've also tried to visualize it in space. Let's say you want to do it for an entire spreadsheet of fluid inclusion. So here's just an example spreadsheet I've loaded in. You can download it from this link if you want to run this notebook. So I've just stored, a sample name, a density, and a temperature I think it was trapped at. So now what you can do is you can basically loop through this entire data frame. So you basically need to say the XH2O that you want to use, the CO2 density, so that's just calling this data frame, and then whatever column you called your density. Same for temperature, and it's going to perform the calculations for the entire spreadsheet. Now this is what a lot of work in the literature has done. In reality, by running degassing models, we know that XH2O isn't constant. It's going to be a function of pressure. So if the fluid inclusion was trapped shallower, in general, there will be a higher mole proportion of water than one that was trapped deeper. So how can we dig into this? Well, let's say you have melt inclusion data. So here we're going to load in melt inclusion data from the 2018 eruption of Kilauea. These melt inclusions, we performed saturation pressure calculations using the model MagmaSat in Vesicle. And that gives us XH2O, or actually we've loaded it in here as XCO2. It's just one minus the other, it's fine. So first of all, let's plot and see what it looks like when we plot saturation pressure against XCO2, or XH2O. As you can see, when we're looking at all of the melt inclusions, we see this really, really sharp increase in the molar proportion of water in the fluid as we ascend towards the surface. Now, it turns out when we looked at fluid inclusions, we don't actually have any in these really, really, really shallow pressures. So we're going to zoom in on the bit of the curve where we really are seeing our fluid inclusion pressures. And what we've done is we've fitted a polynomial through this, okay? So what this means is now for a given pressure, based on melt inclusions, we can predict an XH2O value. So now what we can do is we can load in some fluid inclusion data from the same system. So this is actually Devitra and Weiser, 2024 now. This was just published in JPL. So we're going to load in their fluid inclusion densities from the same system that we have these melt inclusions for. Now, this is a bit of a looping problem in that we have a pressure from the fluid inclusion using the pure CO2 equation of state, which we can then use to calculate an XH2O value, which we would then use to calculate a pressure using the mixed CO2 equation of state, but then the pressure has changed, so we're going to move slightly on this graph. So how we're going to deal with this is we're going to iterate. So first of all, we're going to calculate the pressure assuming a pure CO2 equation of state. We're then going to calculate XH2O. We're then going to calculate a pressure using the mixed equation of state, calculate an XH2O, and we're going to do that 10 times. That's enough to converge in our experience. Okay, so that's what we're basically doing here. So we are calculating an initial pressure using XH2O is 0. We are assuming just a fixed temperature here for simplicity. You can also load in the temperature, and actually in this paper we use a forced-right thermometer to get temperature, but this is just a simple example, so let's just roll with this. So we're going to calculate H2O for that pressure, and this is using the polynomial that we fitted up above here, and you can just see this is where we actually produce that polynomial based on the data. We then calculate a pressure from that H2O value, and then we loop back and we calculate H2O, a pressure, H2O, a pressure, and we do that 10 times. That's what this for dash in range 10 means. Okay, so let's plot it. So we're going to plot H2O against P initial over P. So this is basically like how much our pressure changes by doing this. So you can see the maximum correction is kind of 8%. So it's not a huge correction, but it's definitely worth doing. Okay, so you're an experimentalist and you're not interested in fluid inclusions at all. Here's why this code might be useful for you. So we're going to load in an Excel spreadsheet of experimental conditions. You can download the example here, you can load your own, whatever. So this is what it looks like. So we have a name for the experiment, we have a pressure, we have an H2O, and we have a temperature. So now we can use this function calprop. So this is calculating the properties for a known P using the equation of state of Duane and Zhang. So we're simply going to tell it our pressure. So that's just the name of this data frame, and then the column you put for your pressure, the temperature, and the H2O. And what do we tell you? Well, we tell you the molar volume, the density, the compressibility factor, the fugacity of water and CO2, and the activity of water and CO2. You can also just do the calculation for a single condition. So instead of bothering to load in a data frame, you can just type in numbers. So you can see at 3 kilobars, 1400 Kelvin, and an H2O of 0.2. For example, the density of the bulk fluid would be 0.579. Any questions? Feel free to reach out.